Hello and assalamualaikum to everyone, especially to our instructor for this courses, Prof. Madya IRTS Dr. Muhammad Azali bin Mat Tumari for this courses Intelligent Control System BEJ 44103. And today we would like to present our assignment for the topic laser distance estimation using MLP neural network, regression using Kinect and FOV data by Google Colab implementation. So our group has consists of 3 members, which is my friends Azafifi and Iskandar and myself, Mashami bin Syed Omar. And I will start but with the introduction. So this project aims to estimate accurate laser distance based on input from kinetic depth, reading and field of view angles. We use two multi-layer perceptron models built in Google Colab using Python and TensorFlow. So the goal is to compare these models and evaluate their accuracy in predicting the reference laser distances. Performance metrics used include mean absolute error and mean square error. So for the dataset description is provided in Excel format containing 3 columns, which is field of view angles, Kinect estimated reading, and laser measure reading. So before the training, we clean all the column names, drop missing values, and normalize all values using min-max scalar. So that's it for me, and I will pass to my friend Ajel to continue the methodology.
Okay, now I will present our methodology using step by step by using Google Colab. Uh, so as you can see here, for the step 1, we need to install the necessary library. We need, for example, here is the IP installer, and for the step 2, we mount our Google Drive to access the dataset file. The dataset contains 3 columns, which is like Xiaomi explained, FOV angle, kinetic reading, and laser distance. We also rename the column for clarity and remove any missing value. For step 3, we need to normalize the data in using min-max scalar so that all input value fall between 0 and 1. This is important because neural network perform better when the data is on the same scale. For step 4, we split the data set into training and validation set. We use 70% of the data for training and 30% for validation using train test split for skip learner. For step 5, we built our first MLP model. It has 2 hidden layers, which is 64 neuron and another is 32 neuron. We use ReLU activation and compile it with the ADAM, which is adaptive movement estimation, and optimize MSE loss. For step C, we built a second MMP model with more neuron and additional hidden layer to see if it perform better. We also use different optimizer called RMS prop, which is the learning rate individually for each parameter. This is especially used when different features like Kinet and FOV have gradient that vary in magnitude. For step 7, we evaluate both models using mean absolute error or MAE. The model with the lower MAE is considered more accurate. And for last step, we visualize the performance. We plot the validation loss over export for both model. We also plotted actual versus predicted value to visually check prediction accuracy. So that's all from me. We'll pass to Iskandar.
Thank you, Azil, for the explanation about the methodology. So I will proceed to the graphical result, which is the result. This is the graph one. In this graph, in this first graph, we can see that the violation loss of 50 epochs for both model 1 and model 2. The blue line represent model 1, and the orange one represent model 2. As we can see, model 2 has a lower and more stable validation loss throughout training. So next one. So this is the graph for actual versus model of prediction. As you can see here, the actual line is a green line, and the model of prediction is a dash line, the red dash line. So in the second graph, we plot the actual laser reading versus the prediction made by model 1. Although it followed the trend, there is some noticeable deviation, especially at a certain distance. As you can see, there is a graph that stick together, which is actual and prediction. This is for the model 1. Next one. So this is for the model 2, actual versus prediction. Finally, we can see that model 2 predictions, the actual line is a green line, and the prediction for this model 2 graph is a blue dash line. And it is actually more closely than model 1. So this tells us that model 2 was more accurate in predicting the laser values across the full range, especially in varying distance. Next one. Okay, this is the graphical result for both model, actual versus prediction. The left one is model 1, the right one is the model 2. This is the visual comparison that confirm the result, and model 2 is more accurate than model 1. And this is for the analysis and conclusion. For the first one, as you can see the previous slide, model 2 is clearly outperform model 1 based on lower MAE and MSE. And the deeper architecture allow model 2 to better learn the relationship between kinetic and laser values. The RMS probe optimizer contributed to the better convergence. And in practical applications, such a model can improve the accuracy of kinetic-based system. And the last one, for the future work, we can explore drop layer, regularization, or larger data set to prevent overfitting and enhance accuracy. So for the conclusion for this assignment one, to summarize all the result, is actually both the numeric metric and the graph show that from the graph that model 2 give better prediction, and this confirm that using the deeper architecture and tuning, the optimizer has a positive impact on model performance. So that's all for our tool. Thank you so much.